All right, so today we are going to look at what is known as composition methods. And in particular, we'll look at the Box-Mueller transform and then what we call some convolutions. And again, this is just a way of generating values from some random distribution, okay? And there's a part of me feels like maybe I don't need to cover this, okay? Because R does such a nice job of generating values from the beta, generating values from the t distribution, generating values from the chi-squared distribution. And how can we go about generating values from these things? And we've covered a few of these methods already. We've talked about inverse CDF, and we've talked about rejection sampling, and these are all very good ways to generate random values. But then there's another set of methods called the composition methods, and these basically use kind of what we know about the mathematical properties of of these random distributions, or these probability distributions. So let's go ahead and take a look here. Okay, so we've already talked about inverse CDF, okay, and here are some well-known compositions, okay, that probably you should have covered this in 100B, like the relationship between the chi-squared distribution and the normal distribution, right? So if you take a random normal value and then you square it, the result ends up being the chi-squared distribution. And so if you wanted to generate values from the chi-squared distribution with 1 degree of freedom, you can just generate values from the standard normal and then square them, okay? And then if you wanted like 4 degrees of freedom, what do? You do 4 of these and you add them together, right? And that we'll see that later on what we call the convolutions, okay? The F distribution is you take kind of these two chi-squared distributed variables, and then you take the ratio between them. So you do chi-squared with m degrees of freedom, chi-squared with n degrees of freedom, and then you do u over m, v over n, and you get this F distribution. Which in of itself is a little hard to wrap our heads around. But when you look at the F distribution, it's got this weird tail and all of this stuff. But ultimately, it just depends on the normal distribution. The normal distribution shows up everywhere. F for Fisher, right? He's like our grandfather for statistics. Okay. And then, the T distribution, which is this ratio, and you guys covered all of this in 100B, right? Okay. All right. So we're going to take a look at the normal distribution, and it's called the Box-Mueller transform. And this is like so cool, but it also breaks my heart a little bit because we don't use this at a practical level, right? So when you ask R to do to generate random normal values, it does not do the Box-Mueller transform because Box-Mueller transform is slightly computationally expensive, and R does the inverse CDF, but the cheater method by using an approximation of the CDF, okay? And it's good enough because it gets you 16 decimals of precision, which is about as much as we can hope for on a computer, at least with 64-bit integers. Okay, so these two guys, George Box, Mervyn Mueller, created this thing to turn random uniform values into a pair of standard normal variables, random variables, okay? And kind of the big idea is we go from a Cartesian coordinate to polar coordinates. So we're going to generate values from 0 to 1 or for random uniform, and then we turn these into kind of polar, all right? And so we're going to generate x and y ideally, okay, this is what we want to get. We want x and y coming from a standard normal distribution, and these are generated independently, okay? So x and y are orthogonal. They have no relation to each other. And because they are independent of each other, their joint PDF is just the product of the two PDFs, okay? So I've got the standard normal PDF for x and the standard normal PDF for y, and I can just multiply them together because they are independent. So if you take away your normal PDF, if you take away the mu, or if you plug in 0 for mu and 1 for standard deviation, you get this, okay? Which is rather quite elegant, okay? It's just basically the normal PDF is e to a negative x squared, okay? And then you got a constant in the front so that it integrates to 1, okay? And it's crazy that this thing, when you integrate it, like, you get the pi constant, right? It's just like all of these transcendental numbers just showing up out of nowhere. But here we go. Okay, so when you combine these two, you get 1 over 2 pi e to the negative x squared plus y squared over 2, okay? And so this is a joint PDF, right? So this is the PDF of the values x and y. X and y are both coming from the normal distribution. All right, so do you guys remember polar coordinates? So you're going to go from x, y into r and theta, okay? So theta being your angle from the x-axis, all right? So that in radians, so that goes from 0 to 2 pi, and then r is basically your radius, all right? And so you can cover the entire basically Euclidean plane using r and theta or x and y. Okay? And then if you remember how we do change of coordinates, okay? So basically what we want to do ultimately is we want our function over x and y, dx dy, to become the equivalent function in r and theta. I'll post these notes up. You can scribble all of these things in your notes too, but I'll post these up as well. All right. So do we remember this? This is like, oh yes. So when we do change of variables, right? You got to use kind of this Jacobian stuff, right? So you got, so f of xy is going to be dx dr and then dy d theta. And then we do this thing, and so this thing, the delta xy over delta r theta is the Jacobian thing, and you get dx, this whole thing, right? So every dx dr, dy dr, and then dx d theta, dy d theta, right? And so if you ask, what is the relationship between x, okay, what is dx dr? It's going to be just cosine theta, okay? And what is dy dr? It's just sine theta. And then what is dx d theta? This is going to be negative r sine theta, okay? And then what is dy d theta? And that's going to be r cos theta. And then the determinant of this thing is going to be r cosine squared theta and r sine squared theta, okay? And then like magic, okay, because cosine squared plus sine squared is 1, this just ends up being r. Okay, so we get x squared plus y squared is r squared. Okay, and so we plug this in, right? So we get the change is xy, and then you do this whole thing reduces to r, okay? And then we replace over here. So our joint distribution, we're going to replace x squared plus y squared with r. And when we do the change of variables, okay, x squared plus y squared times r, and then we multiply it in. We multiply that thing by, this Jacobian, or basically how x changes with respect to r and how y changes with respect to theta here. or how x and y change with respect to r and theta, okay, which is this right here. When was the last time you guys touched this stuff? Yeah, okay. It was like your freshman year when you took like 31B or something, right? So I know, it's been a while. It's been a while, and I don't touch this until I do this once a year. So, okay, so anyway, so here we are, okay, and then, so we've got this, and then, so this thing, dr d theta, is this, and we want to go, so we're going to do another change of variables, okay, where we're going to go from r and theta to r squared and theta, okay, because what we're trying to do is we're trying to get these things to be uniform, right? So we're going to go, you know, r can be any value positive because it's the radius measure, and then theta can be any value between 0 and 2 pi, okay? So dr squared is 2r dr, okay? So r dr becomes 1/2 dr squared. So we're going to just replace r dr with 1/2 dr squared. Okay, so this is what we have here, and this becomes e to the negative pi 1/2 dr squared d theta. Okay, and we can split this into a product of this and this. All right, so you can look at this, make sure I'm not cheating here. Okay, so we're going to split this. Okay, we're going to split. So remember, this used to be the joint distribution of x and y as normally distributed variables. Okay, and then we changed the coordinates to r squared and theta. Okay, and so here, okay, like if in your brain, just replace r squared with like j or k or, you know, p or some other number, right? So this is, you know, 1/2 e to the negative p over 2 dp, and this is 1 over 2 pi d theta, okay? All right, so this, if we just look at 1 over 2 pi, that is equal to the PDF of a uniform random variable, okay? Going from 0 to 2 pi. And then if we look at this part, this is, like if you just replace r squared with just some arbitrary letter like p, okay? That would be the PDF of what? Of a exponentially distributed random variable with where lambda is 1/2, okay? Because the PDF of an exponential is lambda e to the negative lambda x or whatever it is, right? So just treat this r squared thing as some thing, and we can say r squared, the r squared value is exponentially distributed with lambda equal to 1/2, okay? Theta is uniformly distributed on the interval 0 to 2 pi, okay? And this also shows that r squared and theta are independent because it's just the product of these two things, okay? So we have shown that the joint distribution of two independent normally distributed variables, okay, if we just take these products and multiply them by applying a change of variables, which granted is a little bit tough, okay, but you know, I've shown you the answer on how to do this. We can demonstrate that this is an exponentially distributed random variable, and this is a uniformly distributed random variable. Okay, and so theta comes from the uniform distribution from 0 to 2 pi, and if we let r squared come from the exponential distribution with lambda equal to 1/2, then we'll get this, okay, and then we can convert that polar coordinate back into x and y, all right? And the whole point is that we know how to generate values from the uniform. That's easy. And we know how to generate values from the exponential. Okay, we did that using inverse CDF. Right. So to do the exponential, we're going to just say theta comes from the uniform. Generate this. Generating values from the uniform distribution is easy. Okay, we'll generate v from the exponential, okay, and then we'll just take the square root of v to be our r, right? And then we convert the values r and theta into polar coordinates to get an x and a y. And x and y will then both be coming from the standard normal distribution. All right, and then we learned how to generate values from the exponential using inverse CDF by doing basically log u, right? You take log u. We did this earlier in like a few class sessions ago, okay? And so you can just say take a random uniform and do -2 log u, okay? And that will be your v value, and you take the square root of that. Okay, so putting it all together, you take two uniform values, okay? Uniform from 0 to 1, and then you multiply that by 2 pi to make it on the range 0 to 2 pi. You generate uniform on 0, 1, and you use inverse CDF, okay? -2 log of whatever this value is, v, -2 log v will be exponentially distributed with lambda equal to 1/2. And then to turn that into the radius, okay, you take the square root of that. And then once you have that, you can do x and y is r cos theta and r sin theta. And it works. It's amazing, okay? All right, so here we can just we can just show this, but ta-da, there you go, okay? You run the code. Here, I'll go ahead and I'll do this right here. Different. Okay, so I guess I'll do, we'll want 1,000 of these things, okay? And so u is going to be, what's going on? R unif, all right? And we're going to take n of these things. And v will also be R unif, and we'll take n of these things. And then, and so theta is going to be u times 2 pi, and our radius is going to be square root of -2 times log of v, okay? So we use u to generate our theta, we use v to generate our r, okay? And then we'll say x is going to be r times sine of theta. Whoops, I should use just a little r here. R times sine of theta, and y will be, or I guess r should be cosine theta. It doesn't really matter, okay? But for, okay, and we'll do r times sine of theta, okay? Here, I'll just do, let's do like 10,000 of these things. Okay, and then let's just make a histogram of x. All right, and indeed that looks normal, right? I can do QQ norm on x. Does that not work? Okay, there we go. And that's about as good as you can get, okay? And if I do the same thing for y, histogram of y, that looks normal. QQ norm on y. That looks good too. All right, and we can do a Shapiro-Wilk test on X. Oh, Shapiro only likes to do for 5,000. Okay, so let's just do the first 5,000 then. Okay, and for the Shapiro-Wilk test for normality, I'm getting a p-value of 0.75, so I have no reason to believe that my data is not normal. Okay, if I do it for the other half, 5,000 through 10,000, okay, I get a p-value of 0.924, so again, no reason to believe that it's not normal. Okay, similarly for with y, I'm getting a p-value of 0.252 and things like that. Okay, so so we can just use u and v, which are random uniform, to generate values from the normal distribution. Okay, and I think it's so cool that you can do, like, if you think creatively about this stuff. And I wouldn't expect anybody to have like thought of this on their own, right? So this is Box and Mueller. They came up with this thing and they published it, and everyone's like, "Wow, that's really cool." And you know, unfortunately, we don't even use it. Like when we do our norm to generate, you know, 1,000 values here. We make a histogram of z, and things like that. Well, the R norm here uses inverse CDF, and it just uses an approximation of the CDF of R. Okay. I did the Shapiro test. You guys learned about the Shapiro-Wilk test? No? Okay. So it's just another test to see if it just gives you a p-value for, does my data look normal, right? So I don't know the exact math behind the Shapiro-Wilk test, okay? But basically, it calculates a statistic, and it will report back a p-value. And so, kind of like the KS test, the Kolmogorov-Smirnov test, if your p-value is tiny, that gives you indication that maybe your data is not coming from the distribution that you specified. And likewise for the Shapiro-Wilk test, if your p-value is tiny, then that might give you indication that your data is not normal. But if your p-value comes back big, then you have no reason to believe that your data is something other than normal. Okay. Again, in statistics, we can never prove that the population has some property or that the population is normal or something like that. But we can say, I looked at a lot of data points, and I currently have no reason to believe that there is no reason to believe that it's not normal. Okay, so there we go. Box-Mueller transform. Okay. All right, and so we can generate values from the standard normal using the Box-Mueller transform. What if we wanted to get other values using a different mean mu and a different value sigma squared? How would you transform a standard normal value to a value from some arbitrary normal distribution?
Times sigma squared plus 1.
Exactly, right? You just do the z-score thing, right? So z-score is, you know, x minus mu over sigma, and then so now you have a random z, and you multiply it by sigma, you add mu. Okay, so that's all we do. All right, so if we have z is this, then we do this. So we just do mu plus sigma times z. Okay, and then the result's going to be normally distributed. Okay, and here's just all of that. Okay, so just quick transformations using, you know, what we know. All right. Okay, convolutions. Convolutions are basically sums of random variables, right? So you just take a bunch of stuff. If each of these x's are random and you add them up, then that's technically a convolution, okay? So you say, you know, all of these things are coming, and you generate a sample and you compute the sum. So kind of the binomial distribution is technically a convolution of Bernoulli results, right? So you can say, because the binomial is directly like, if I flip the coin 10 times, how many times did it land heads, okay? So basically, to do a convolution, you would just generate 10 Bernoullis of coin flips, and then you add those up, and now you got a binomial variable, okay? And that's that, okay? So, so here we have it, right? So a binomial is just kind of the sum of Bernoullis, right? So you do a bunch of coin flips. Bernoulli is a coin flip, and you either get a 1 or a 0. And then if you add those up, if you do it m times, okay, then you've got a binomial distribution with parameters m and p. All right, and then there's a whole bunch of other things that are convolutions, right? So Poisson, a Poisson is if you have x be a Poisson variable, then you can do the sum of x's, and that will be just another Poisson variable, right? So so this will be so if x is Poisson with rate parameter lambda, and they're all independent Poisson random variables, okay? Then you can kind of add up these things, and you'll have a Poisson distribution where the mean is the sum of the lambdas. So it's just, so when do we use the Poisson distribution? How many events happen in a certain interval of time, right? So you guys know about like the Prussian horse kick data set? Okay, no, all right, Prussian cavalry? All right, so it's kind of, it's a little bit morbid if you think about it, but okay, so, you know, there used to be the Prussian military. Who did Prussia turn into? There's like kind of this Germany/Polandish thing, right? So you got the Prussian military, and they had the cavalry, and they ride horses, and occasionally a soldier on a horse will fall off. You know, their like feet are stuck in the stirrups, and then they get kicked to death by the horse. Okay, and it's funny, kind of sounding, but also horribly grim, right? So, but anyway, they were just trying to figure out like, well, how often does this happen? And you can just think of it as kind of each event is a little bit random. So each event is just it's random uniform. It's not like it's more likely to happen over here or more likely to happen at some other time. They're just randomly uniform, but when you count how many times a random uniform thing happens within a certain interval of time, it's going to follow a Poisson distribution. So so anyway, that's what it is. And so you can generate one value from Poisson, and then and if you do a whole bunch of these things, then you'll have a mean parameter with something bigger, right? So it'll be if you expect 3 pieces of mail to each day, and you want to say, well, what's going to be the result from the full week of 7 days or something? I guess mail doesn't come on Sunday, so 6 days. So you can do you can add up the Poissons for 3 things. Okay. All right, the negative binomial. You can generate things from the geometric, add them together, and get the negative binomial. Chi-squared distribution. You can just take individual chi-squared things, add them up, and you'll get a chi-squared distribution with m degrees of freedom. So if you have each thing is, you know, normal from this, each one's going to be chi-squared with 1 degree of freedom, and then if you add them up for m of these things, you get the chi-squared distribution with m degrees of freedom. And so, you know, I think, don't take my word for it, right? So we can do z as our norm, okay? I mean, technically we could take the x's that we've already created, right? So I've got x, and this is normal, okay? So I can take each of these x's, and I can square them, okay? And then we'll call these chi-squares, okay? And so if I do a histogram of the chi-squared values, then this should be follow a distribution with chi-squared, a chi-squared distribution with 1 degree of freedom. Okay, and we can kind of test this out. We can see, you know what? Let's do density of the chi-squared values. Plot this. It's a density estimation of this. Okay, and so this is what it looks like. And does that, and let's also look at the empirical CDF of the chi-squared. Okay, and that looks reasonable. Okay, and we can compare this to, say, the sequence will go from, say, 0 to 15, and oops, and let's do y equal to 0.01. Okay, and then we can calculate, we'll call this theoretic chi-square PDF. I'll just call this chi-square PDF, all right? And this will be P norm of S, okay? And then we're gonna say, not P norm, I'm sorry, P chi-square of S, and I think by default, P chi-square, I think by default it has 1 degree of freedom. Oh no, I have to specify, okay. With df equal to 1. Okay, so we'll go ahead and do that, and we'll plot, we'll add the theoretic one to this. Okay, so we'll do lines of S and chi-square PDF, color equals red. Okay, and that lines up like almost perfectly, right? Okay. I don't know if I can do a KS test with 10,000 things. KS test, and we'll compare chi-square versus P chi-square with and df equal 1. Okay, so when I do that, okay, it worked fine, and I get a p-value of 0.88. So that seems good. All right, and if we wanted to do chi-square distribution with, say, 5 degrees of freedom, okay, then I'm going to have to, what I'll do is I'll make a chi-square matrix, right? I'm going to take all of my chi-squared values, I'm going to just turn it into a matrix. I'm going to just take chi-squares, and then we're going to say number of columns is equal to 5, okay? And then and I'll have chi-square df5, degrees of freedom 5, will just be kind of our row sums of my chi-square matrix. Does that make sense? So I'm just taking all of the chi-squared values, and then I'm just arranging them in a matrix. So each row will have 5 chi-squared values, and then we're just going to sum them up, doing our row sums. Did that work? Okay. And then, all right, let's go ahead and plot all of these things, but now with 5 degrees of freedom. Chi-square df5. All right, that looks reasonable. That's that. And the so this is our density estimate, and this is our empirical CDF. Here we can plot this, and then I'll just add lines of S versus d chi-square of S and df equal to 5, and color red. Oh, parentheses in the wrong spot. Okay, so the red is the theoretic PDF, and the black line is my empirical PDF. All right, so that seems reasonable, and I can add this. Lines, we want the chi-square PDF, whoops, with 5 degrees of freedom. Something wrong. Okay. Oh, I'm sorry, p chi-squared. It's bad habits. All right, p chi-squared, s, degrees of freedom 5, okay? And so we do that, and again, they line up almost perfectly. We can do the ks test of chi-square df5 with p chi-square and degrees of freedom equal to 5, okay? Chi-square df5, okay? And we get a p-value of like 99. So no reason to believe that our data is not from the chi-square distribution with 5 degrees of freedom. Okay, and so, and of course, it's a little bit silly because R has this really good R chi-squared thing, right? So if I do R chi-square and I could ask for 1,000 of these things and say df5, and it's going to generate a whole bunch of these things, and it's going to be perfect. Actually, I never looked at what is the thing. Okay, so unfortunately, we cannot see how R chi-squared works because it calls a C function. The function's written in C called C R chi-square. So we don't get to see the inner workings of this, which is too bad. I think our norm. No, it also doesn't tell us. Okay. Doesn't tell us the inner workings. A lot of these things you can plug in, write the name of the function, and you'll at least see the call, and stuff like that. Okay, but you can generate all of these things. The gamma distribution is basically the sum of exponential distributions. So it's just if the time for one customer to arrive is 20 minutes, what's the time it will take for 5 customers to arrive, okay? It's just the sum of 5 exponentially distributed things, okay? And so that ends up being your gamma distribution there. Okay, and then, and so things get even more complex, right? So the beta distribution can actually be written as the sum of a bunch of exponential things. And so here, so notice how we do this. You are generating a total of a plus b values from the exponential. Okay, and so you get 1 through a, and then a plus 1 through a plus b. Okay, so this is basically 1 through a, and then this is technically like 1 through b, but it's starting at like, you know, see if you want like 50A and 50B, you're going to generate 1 through 50 and then 51 through 100. Okay, and then you do the sum of the first 50, the A ones, the 1 through 50 go on the top, and then you put all of them in the denominator, 1 through 100 in the denominator. Okay, and then when you do that, that ends up being beta distributed. Okay, and if you look at this numerator, because it's the sum of exponentials, is just a gamma distribution, right? So you got a gamma of A, all right? And then down here, this thing is going to be the sum of A plus B, all of them. And then so that's basically just the gamma with alpha and the gamma plus the gamma of beta, okay? I'm not sure if I'm going to throw this in a homework or not. If I do, one common mistake students do, like let's say I say A is 50 and B is 50, okay? A common mistake students do is that they will do generate 50 for A, generate 50 for B, but then when they do this, they just generate like an entirely separate like 100 values or something like that, okay? And you're using the same. So what you're doing is you're generating 50 for A and 50 for B, and you're gonna use the 50 for A in the numerator, and then you use the same 50 go into part of the denominator, and then the remaining 50 from B go into the denominator. Don't generate a whole nother set of this, okay? Because that could potentially lead to a situation where you get a value greater than 1. But the beta distribution is always between 0 and 1 here. Okay. All right. Well, we'll just cover convolutions. I'm not going to bother covering the mixtures of normal distributions just yet. But we'll stop here, and we'll see you guys on Friday, and you can expect your midterm grades posted sometime tonight. So.